Okay, imagine this. Picture it playing out. Maybe even right now. You've got this powerful hurricane, just this massive swirling thing, and it's heading straight for the coast. Densely populated coast.
Millions of people.
Millions. And they're all hanging on, bracing themselves, relying completely on those forecasts. Absolute precision needed for, well, life-saving decisions. Evacuate, shelter.
Analyzing decisions, yeah.
And then, boom, just like that, no warning, one of our most critical eyes in the sky, this vital window into the storm's heart, it just goes dark.
Just switched off.
Switched off. Welcome, everyone, to Meteorology Matters. We're your guides today, and our mission, like always, is to take this, well, complex, sometimes really daunting information from all sorts of places and really distill it down, make it clear, give you actionable insights.
Yeah, the goal is to help you become genuinely well-informed. Not just the headlines, but the actual science shaping things.
Exactly. And today, we're digging into a really sudden, very impactful, honestly, kind of mysterious decision. Came down just this week from the United States Department of Defense.
Unexpected, is putting it mildly. They've decided to just terminate the processing and delivery of absolutely vital data. Data streaming from a specific set of weather satellites.
We're talking about the Special Sensor Microwave Imager Sounder, or everyone calls it SSMIS.
Yes, SSMIS, yeah. That's the one.
And let's be crystal clear here. This isn't some, minor technical tweak only specialists care about. No. This is profound. It's like a seismic shift in how we observe these storms.
Absolutely. It's a move that's going to severely impede, significantly degrade hurricane forecasts. And not just for this year, the 2025 season that's starting now, but way beyond. Future seasons, too.
We're talking direct impacts, tangible, tens of millions of people living along those coastlines, their safety, their economic well-being. It relies on accurate predictions.
And what's really baffling, truly perplexing, is the lack of any immediate, clear reason. Why now? Why so abrupt?
It seems to be tangled up with Department of Defense security concerns. But the really alarming part, even top officials at the National Hurricane Center were completely blindsided.
No heads up. Nothing. Caught totally off guard.
Yeah, it's just wild.
It's unprecedented, really. And the ripples are already spreading through the whole weather and climate community. So over the next little while here on Meteorology Matters, our job is to dive deep, figure out exactly why this data from SSMIS, why it's so uniquely vital.
Right. What are the concrete impacts going to be? Its loss, on understanding, tracking, preparing for these massive weather events, hurricanes, climate patterns.
And critically, what's the path forward? Because the global meteorological community is scrambling now, almost frantically, trying to adapt to this sudden hole in the data. So let's unpack it.
Absolutely. Let's peel it back.
Yeah.
Because to really get the gravity here, you first need to appreciate the absolutely essential role microwave satellite data plays in forecasting hurricanes. It's intricate stuff.
And hurricanes themselves, they present this fundamental challenge for observation. It's plagued meteorologists for, forever.
Decades, yeah.
Yeah.
These huge storms, they mostly form and get stronger over these massive stretches of open water. Think about the scale. Hundreds, thousands of miles from land.
Where you just can't put ground measurements. It's not feasible.
Right. No weather stations out in the middle of the Pacific or dotted across the deep Atlantic. We just don't have them.
Exactly. That's the core dilemma. And yeah, we have the Hurricane Hunter planes, those amazing, brave crews flying right into the eye.
Incredible data from them.
Invaluable, but they have real practical limits. These planes, they're only available for about 1 out of every 3 Atlantic hurricane forecasts.
1 in 3. Wow.
Yeah, think about that. 2/3 of the time, we don't get that direct granular data from inside. And for Pacific storms, almost never, maybe a handful of the really extreme cases.
So most of the time, for these huge ocean storms without those planes, we're kind of flying blind, making critical calls with way less information.
Essentially, yeah. It leaves this huge observational gap, a void that desperately needs filling for accurate forecasts.
And that's where the satellites come in. But here's where it gets really interesting, where the power of this specific data, the stuff we're losing, really shines.
There's a key difference, right, between the satellites most people are familiar with, ones giving those beautiful swirling cloud pictures.
Yeah, the geosynchronous ones you see on TV.
Exactly. Those versus the more specialized polar orbiting satellites carrying these microwave sensors.
Okay, so what's the difference? Those regular visible or infrared satellites, they're great for tracking clouds, seeing the storm top.
But they struggle. They can't really see through the dense clouds. especially at night when visible light is gone anyway.
Ah,
So they often completely miss crucial details, stuff happening inside the storm structure, changes that can signal dangerous rapid intensification. You just can't see the inner workings with those conventional tools.
right. You only see the surface, the top layer.
Precisely. Yeah. And what's remarkable, what makes microwave data indispensable, is it gives us this unique capability. It's almost like an MRI scan of the atmosphere.
An MRI. Okay, I like that analogy.
Yeah, like a doctor using an X-ray or MRI to see through tissue to the organs inside. That's what microwave satellites do for us.
Yeah.
They let forecasters literally peer through the obscuring clouds, through the heavy rain, right down near the surface.
So they can see the storm's inner workings.
Exactly. Where the heaviest rain is, the actual center location, and critically, its thermal and moisture structure. And they get these updates every few hours. It reveals what's happening inside, even when it's totally hidden by clouds.
That's the X-ray vision you mentioned, seeing the internal heat, the moisture, stuff the normal pictures miss.
It's the difference between seeing a car's paint job and understanding how the engine works. It's that level of insight.
Okay, so let's zero in on the instrument itself, the one going dark. SSMIS, Special Sensor Microwave Imager Sounder. Break that down for us.
Okay, so it's a conical scanning passive microwave radiometer.
Whoa, okay. Conical scanning.
Yeah, imagine a sensor spinning like a lighthouse beam, sweeps around, but it's looking down, sweeping this wide, cone-shaped path below the satellite as it orbits.
Got it. And passive.
Passive means it's not sending out its own signal like radar does. It's just listening to the natural microwave energy that the Earth's surface and the atmosphere, including the storm, emit naturally.
Different things emit different signals.
Exactly. Water vapor, rain, ice particles, they all have unique microwave signatures. And this instrument picks them up across 4 main frequencies, 19.3, 22.2, 37.0, and 85.5 gigahertz. And it uses 7 specific channels within those, with different polarizations too.
Like different channels on a radio, tuned to different things.
Kind of, yeah. Think of them as different wavelengths, each tuned to see different aspects. Lower frequencies are good for heavy rain. 22.2 gigahertz is super sensitive to water vapor, and that 85.5 gigahertz one. That gives incredible detail on ice scattering deep inside the storm core. Really vital for structure.
And this tech isn't brand new, right? You mentioned predecessors.
All right, the first one, the SSMI, launched way back in June 1987, part of the Defense Meteorological Satellite Program, DMSP. So this capability, it's been foundational for decades.
And that history, that long record, makes this loss even more significant. These DMST satellites with SSMIS, they orbit in a specific way.
Yeah, near constant 53-degree angle, about 830 kilometers up. And this geometry lets them collect consistent data over a really wide path, about 1,400 kilometers across.
So each pass covers a huge area.
A huge area, giving comprehensive observations. And the resolution, how much detail we get. It's 25 kilometers for things like total water vapor and sea surface wind, and 5 brightness temperature channels. But for that crucial 85.5 gigahertz channel, the one giving the sharpest internal view, it's even finer, 12.5 kilometers.
So those aren't just numbers, are they?
Yeah.
That defines the quality the detail forecasters have relied on.
It's high-definition storm diagnostics, absolutely invaluable.
So what do forecasters do with all this detailed, penetrating data, beyond just cool images?
Oh, its contributions are indispensable, huge for accuracy. For starters, it's critical for precisely fixing the storm center, pinpointing it exactly.
That sounds simple, but you're saying it's not.
It's notoriously difficult with just visible or infrared, especially if the center is hidden under a big cloud shield, which often happens, like finding a needle in a haystack in the dark. Microwave lights up that needle.
And getting that position right is crucial because
it directly fights that butterfly effect we mentioned. Even small errors, maybe just tens of miles off initially for a weaker storm.
they blow up over time.
Dramatically. That tiny initial error, if you don't correct it with precise microwave data, it cascades into outsized forecast errors 4 or 5 days later. Big misses in the track forecast.
But where the storm actually goes, that initial pinpoint matters that much.
Immensely. It's like aiming that billiard ball off by a millimeter at the start. You're way off down the table. Without SSMIS, that initial millimeter error is much more likely.
Wow. And it also powers some advanced tech, AI stuff.
Absolutely essential for that. One of the key tools for estimating storm intensity, especially when the hurricane hunters can't fly, is called DMINT, Deep Multispectral Intensity of Tropical Cyclones Estimator.
DMINT sounds powerful.
It is. It uses AI to analyze satellite data and predict storm strength. And it relies heavily, almost entirely, on the microwave data it ingests, Without SSMIS DMINT's ability to give accurate, timely intensity estimates, severely hampered. Forecasters lose a key intensity tool.
Leaving them less certain about the storm's true power.
Exactly. And that directly increases the risk of what James Franklin, a retired NAC branch chief, famously called a sunrise surprise.
A sunrise surprise. Sounds ominous.
It is. It's that horrible moment seeing the first visible satellite pictures at dawn and realizing a storm got way stronger, way better organized overnight, maybe intensified dramatically.
But you didn't see it happening.
Because the key structural details were hidden from the infrared views overnight. Details only microwave data would have shown. It's finding out too late that the storm ramped up, giving people much less time to prepare for something far more dangerous.
That's terrifying, and that scenario becomes more likely now.
Much more likely. That microwave data was our safeguard against it.
So the bottom line here, the immediate impact. DMSP, these 3 satellites with SSMIS, they provide roughly half of all the microwave scans forecasters get.
Roughly half, yeah. Globally.
And with the DoD pulling the plug on processing by June 30th, that vital data stream just goes dark.
Poof. Gone.
It's like a surgeon suddenly losing half their x-rays mid-operation, or a pilot losing half their instruments on approach.
It's that level of challenge for hurricane forecasters now. This isn't just an inconvenience. The very data that helps spot those sudden, terrifying bursts of rapid intensification.
When a tropical storm explodes into a Cat 3 or 4 overnight,
that early warning capability is severely compromised. Data availability sliced in half. It just greatly increases the odds of missing these events, underestimating storm strength, misplacing centers. It degrades forecast accuracy, period.
It's a huge blow to hurricane preparedness. And it inherently puts more people at risk, right? Could cost people more money dealing with worse forecasts.
Absolutely. More risk, potentially higher costs for everyone involved. Individuals, communities. Dealing with degraded forecasts has real consequences.
And this isn't just about hurricanes, is it? The impacts spread wider.
Much wider. This data termination sends ripples everywhere, including critical climate monitoring, especially for sea ice in the polar regions.
Sea ice, how does microwave data help there?
Well, SSMIS data is fundamental. It's a core input for key data sets from the National Snow and Ice Data Center, NSIDC, run by the National Oceanic and Atmospheric Administration. Things like their near real-time sea ice concentration records, the overall sea ice index, crucial for tracking climate change, Arctic navigation.
And those products rely on SSMIS.
Heavily. And the immediate unsettling consequence. Those specific products just stopped processing after June 30th, 2025. Users, scientists, shippers, northern communities, they have to anticipate a data gap.
Like losing a key chapter in the climate story makes it harder to see the whole picture.
It's a major disruption for climate science. And navigating it, well, there's this urgent scramble to find and integrate alternatives. For products built purely on SSMIS, like sea ice concentration OSI 401D and the interim record OSI 430A, users just have to switch. Find new products based on different data.
Which isn't simple, right? Requires validation, introduces uncertainty.
Exactly. Takes time, resources, not a clean swap.
But some products are okay. You mentioned multi-sensor ones.
Yeah, there's a bit of a silver lining there. Things like Sea Ice Edge, Type, and Drift OSI 402D, 403, 405D, they use multiple sensors already.
Yeah.
And another instrument, AMSR2, is their primary source, so they're more resilient. They'll keep working without SSMIS.
Okay, so they had a backup plan, essentially. That's fortunate.
Incredibly fortunate for those specific applications. And other products like Sea Ice Emissivity and L2C Ice Concentration, they're either actively migrating to use AMSR2 data now, or they already offer AMSR2 versions that users are being urged to switch to.
So there's a push to adapt.
A huge push. And what's really critical for the long-term climate picture is things like the Sea Ice Index, OSI 420. They're undergoing complex changes to integrate AMSR2. The absolute goal is a continuous time series, seamlessly building on the old SSMIS data.
So we don't lose track of the long-term trends.
Precisely. That continuity is vital. It's a massive effort, but essential to preserve decades of climate records.
Okay, so we've covered the practical impacts, hurricanes, climate. Let's really dive into the science now. Data assimilation, why this specific data loss hurts so badly.
Right. At the very foundation of all-weather prediction models, these incredibly complex computer programs generating forecasts, is this absolute reliance on accurate initial conditions.
Starting point.
Exactly. Precise data on the atmosphere state right now, especially moisture. Think of it like setting up dominoes. If those first few are off even slightly,
the whole chain falls apart unpredictably.
Perfectly put. And this is where our conventional observations weather balloons launched mostly over land, twice a day. Surface stations, also mostly land-based, just fall short, especially for fast-changing storms over the ocean.
They're too sparse, too infrequent for hurricanes.
Entirely inadequate for sampling those dynamic, moisture-rich environments over the vast oceans. And even tiny uncertainties in that initial humidity field, which is super hard to measure globally, they can have a huge detrimental impact later on in the forecast. Errors grow exponentially.
Which is where satellites become absolutely essential, irreplaceable even.
Totally. Unlike fixed points, satellites sweep across the globe, filling those massive ocean gaps, providing spatially dense, repeatable data where we had almost nothing before.
From scattered snapshots to a continuous global video feed.
A great way to think about it. Now, getting all this indirect satellite data, not direct temperature or pressure, but microwave signals into the models, that requires sophisticated techniques, data assimilation. Specifically, things like 3D VAR, three-dimensional variational systems.
3D VAR, okay, break that down.
Imagine the atmosphere as a giant, complex puzzle. Our models predict how the pieces move. Traditional observations give us some pieces, but there are huge gaps, especially over oceans. Satellite data floods us with new clues, often indirect clues like microwave brightness temperatures.
So 3D VAR is how we fit those clues into the puzzle.
Exactly. It's like a super smart digital detective. It takes all observations, balloons, satellites, everything, and mathematically finds the single most consistent and most probable picture of the atmosphere right now. It optimizes the initial conditions, gets the puzzle started as accurately as possible.
So the rest of the prediction works better. And there are different ways to feed SSMIS data into this.
Two main ways, yeah. First is assimilating retrieved products, or RV.
RV, what's that?
It's computationally faster. You first convert the raw satellite signals into geophysical things like total water vapor or surface wind using statistical algorithms. Then you feed those into the model.
Quicker, but maybe less accurate.
Potentially. Because those statistical conversions, those retrievals, they might have errors or biases if the statistics aren't perfect, or if other info used in the process is flawed. It's an estimation.
Okay, so what's the other way?
The second method is directly assimilating the raw measurements, the brightness temperatures, or TB.
TB raw data.
Right. This is more computationally intensive but more physically robust. You feed the raw microwave signals directly into the model using a complex radiative transfer model. This simulates how microwaves actually travel through the atmosphere.
So it's based more on physics than statistics.
Exactly. Less dependent on potentially iffy stats, better at reducing systematic biases. It takes more computer power, but often gives a purer, more accurate starting point because it uses the fundamental physics.
More complex, but potentially better results.
Generally, yes. And the math works out well enough to make it feasible.
Okay, to really hammer home why this matters, you mentioned a case study, Hurricane Danny.
Yeah, Hurricane Danny back in July 1997. Fascinating storm, formed from a non-tropical system intensified in the Gulf. A perfect real-world test bed for seeing the impact of SSMI data assimilation.
So what happened in the baseline? The forecasts without the microwave data. The control case.
The results were stark. Pretty alarming, actually. The initial conditions from standard systems like NOAA's GDAs, they severely lacked moisture over the Gulf. And the storm's initial spin, the low-level circulation, was way too weak.
Which led to
big underestimates of intensity. For example, the model's central pressure for Danny was 19.5 hectopascals higher than observed after 48 hours. A huge miss.
Right.
Plus, the model needed at least 8 hours of spin-up time before it even started raining, realistically. It was starting cold.
8 hours just to get going properly. That's a long delay.
A very long delay. But here's where the SSMI data made a transformative difference. When they assimilated either the retrieved products, RV, or the raw brightness temps, TB.
What changed?
Instantly, almost. The atmospheric moisture across most of the Gulf dramatically increased in the model's starting point. The low-level circulation got much stronger, much more realistic. The inflow feeding the storm improved.
It gave the model the right ingredients from the start.
Exactly. And crucially, that spin-up time. It plummeted. With SSMI data in, the model started producing light rain within just 1 or 2 hours.
Wow, from 8 hours down to 1 or 2. That's huge for getting timely rain forecasts out.
Massive. And the intensity forecasts. They got incredibly better, much more accurate at capturing the storm's deepening pressure. The raw data, TB approach, got the final pressure within 1 hectopascal of reality after 48 hours. The retrieved data, RV, was 8 HPA deeper than observed, still vastly better than the control's 19.5 HPA error.
So both methods were dramatically better than no data at all. A revolution, really.
Absolutely. And the visual structure in the simulations. Night and day. With SSMI, the models produced clear hurricane eyes, distinct eye walls, spiral bands, which is totally missing in the control run.
Like seeing an ultrasound versus just guessing?
A perfect analogy. Forecasters could suddenly see the storm's internal evolution much more clearly.
Now, what about the computational cost? All that raw data processing sounds expensive.
You'd think so, but the study actually showed that while the raw TB method took about twice the CPU time as the RV method, the total assimilation time was still only about 3.5 minutes, compared to the 157 hours it took to run the 48-hour forecast itself. Negligible.
So it's totally affordable, computationally speaking, a tiny investment for massive forecast improvement.
Completely affordable and highly beneficial. It pays for itself many times over in improved warning.
But it wasn't a magic bullet for everything, right? The study noted some limitations.
True. While intensity and structure improved dramatically, the impact on the storm track forecast was surprisingly small. All the simulations, even with SSMI data, had this consistent leftward track bias. They predicted Danny to go slightly left of where it actually went.
And that matched the official forecasts at the time.
Yeah, suggesting a deeper issue. Probably inaccuracies in the initial steering winds higher up in the atmosphere.
Stuff that SSMI doesn't directly measure well.
Exactly. It points to the need for other instruments, like LIDAR, that can measure those steering winds directly. You need complementary data. And even with SSMI, the models still struggle to capture every cloud band perfectly, or subtle things like cirrus clouds. No single instrument sees everything.
It's always about combining perspectives.
Always. But the key takeaway from Danny is undeniable. Assimilating that SSMI data had a strong, unequivocally positive impact, especially on intensity and structure. While the two methods, RV versus TB, had differences, both were vastly superior to having no data. It proved this microwave data is foundational.
Foundational, not just incremental. Okay, so laying all that out, knowing its value, what's the path forward now? We have this immediate, lasting data gap.
Yeah, and it casts a long shadow over this hurricane season and beyond. Losing SSMIS means losing half our microwave instruments. It dangerously increases the odds of missing rapid intensification, underestimating intensity, misplacing storms.
Putting more people at risk, increasing potential costs.
Plain and simple. But the community isn't just sitting back. They're urgently searching for replacements. The main contender right now is AMSR2 Advanced Microwave Scanning Radiometer 2.
AMSR2, does it offer improvements?
It does. Better resolution than SSMIS, so potentially more detail. That's good.
There's a catch.
There is. AMSR2 data is still considered prototype. It's undergoing testing. And crucially, it hasn't been fully intercalibrated with the older SSMIS data yet.
Meaning the measurements might not line up perfectly.
Exactly. Users might see differences, say in CI610, comparing AMSR2 to the historical SSMIS record, partly because its higher resolution sees edges better. So while it's promising, it's not a seamless swap yet. It's a work in progress.
And progress takes time we don't necessarily have right now. What about other options?
There's the Weather System Follow-on Microwave, WSF-M, designed specifically as the successor to DMSPS SMIS. It launched successfully in April 2024.
Fantastic. So that should fill the gap.
It should. But here's the frustrating part. The data from WSF-M is not currently available to forecasters.
Wait, it's up there, but we can't use the data.
Correct. It's uncertain if or when access will be permitted. Bureaucratic hurdles, security protocols, complex reasons. But the bottom line for forecasters, a capable satellite designed for this exact purpose is flying blindfolded right now. The data isn't flowing.
That's incredibly frustrating. So connecting this all back, the broader stakes for society are huge.
Undeniable. This data loss puts more people at risk. It could lead to higher costs, unnecessary evacuations, or worse, failing to evacuate when needed. The ripples hit emergency services, insurance, supply chains, daily lives.
It really underscores how much we rely on this infrastructure. On a slightly brighter note, anything happening right now?
A tiny, fleeting positive. Current models show the Atlantic staying quiet through the end of June. No tropical development expected for the next week or so.
Okay, so a small window of reprieve as this data stream shuts down.
A small window, but just a brief calm before what could be a very challenging, very unpredictable season, now with fewer tools in the toolbox.
So to wrap up our Meteorology Matters discussion today, we've looked at the sudden, really impactful loss of critical SSMIS data, an indispensable eye in the sky, now dark.
We've detailed the profound implications for hurricane intensity forecasts, for vital sea ice monitoring that tracks climate change. And we've looked at the urgent, ongoing scramble to find, test, and integrate alternatives to fill this sudden gaping hole in our observations.
And this whole situation, it really makes you think, doesn't it? It raises a question for you, our listener. How often do we really stop to consider the complex, often invisible scientific web that supports our safety, our economy, just our daily lives?
Yeah. What other crucial unseen data sources are we just assuming will always be there? Data that, like SSMIS, could just vanish overnight.
Mm.
And what's the real cost of unquantifiable when these critical systems are disrupted? Something to ponder.
Definitely something to ponder. Now, if you want to stay right on the cutting edge of meteorology, hurricane tracking, and keep getting clarity on vital topics like this,
You absolutely need to follow meteorologist Rob Jones. You can find him on Instagram. Just search meteorologist.
he's also on TikTok as TV meteorologist.
And definitely check out his YouTube channel. Search Rob Jones Hurricane. That's where you'll also find the Meteorology Matters podcast playlist with all our discussions.
Excellent resources. Well, thank you for joining us on this Meteorology Matters deep dive.
We look forward to exploring more essential knowledge with you next time.